In this lesson, I'm going to cover everything you need to know regarding SN1 and SN2 reactions. So we'll talk about substrate effects and nucleophile effects and solvent effects and what makes a good leaving group and things of this sort. And especially we'll distinguish, given a set of reactants, how you distinguish between SN1 versus SN2. How do you know which mechanism you're doing? And then especially how do you predict your product? We'll definitely end this video by working several examples. So, and if you're looking for more practice after that, check out chadsprep.com. So if you want to be notified when I release more of these, be sure to subscribe or not. All right, so before we dive in, we definitely just got to take a little time to talk about what does a substitution reaction even look like and who are the players we'll talk about here. So these are called nucleophilic substitution. So, and we'll be the thing doing the replacing, the thing doing the substituting will be called a nucleophile here in blue. And what it will be replacing here, I've got abbreviated LG for leaving group. So, and the reactant with the leaving group is often either called the electrophile, since it's reacting with a nucleophile, or more commonly the substrate, which is the term I will use here. And so we can see here in our substrate, our nucleophile reacts with our substrate, replacing the leaving group, and now the leaving group's been kicked off and is all alone. Now, turns out to be a nucleophile, your big hallmark to be a nucleophile is going to be a lone pair of electrons. Now, that's a really vague definition, and once we get into SN2 and SN1 specifically, we'll get a little better idea of what these nucleophiles look like. And then your leaving group, the big thing is that your leaving group needs to be stable on its own after it leaves. And the larger halides, chloride, bromide, iodide are the most common leaving groups by far, but we'll see a couple others along the way as well. Let's take a closer look at SN2 reactions. So the first substitution reaction we'll talk about is SN2, and SN2 stands for Substitution Nucleophilic Bimolecular. And the bimolecular term is really a kinetics term. It refers to the fact that there's two reactant molecules involved in the rate determining step, the slow step of the reaction. In SN2's case, that's usually the only step in the reaction, we'll find out. And in this case, because those two molecules are both involved in that rate determining step, they typically both show up in the rate law. So we took a typical rate law here for an SN2 reaction. We see that both the nucleophile and the substrate show up. First order with respect to the nucleophile, first order with respect to the substrate. Those are the exponents, if you might recall from Gen Chem. So when there's no exponent written, it's implied that it's a 1, and the overall the overall reaction order is just those individual orders added together. So first order for the nucleophile, first order for the substrate, second order overall. That's where that 2 again comes from. Bimolecular rate laws always are second order rate laws. All right. So keep in mind that 2 does not refer to the number of steps in the reaction. So, because most SN2 reactions are a single step, we'll find out. But it does refer to how many reactant molecules are involved in the rate determining step. All right, so we take a closer look at an example here. So here I've got 2-bromobutane reacting with sodium cyanide and acetone. And in this case, 2-bromobutane is our substrate. Let's write that out. So bromide is a good leaving group, it turns out. So we stated that a little bit earlier, and the idea is that, you learned in Gen Chem HBr is a strong acid, so Br minus, the conjugate base, is a super, super, super weak conjugate base, and that's the hallmark of a good leaving group. I want it to be really stable after it leaves, and an indication that it's really stable is that it's a really weak base. All right, so in this case, it turns out the hallmark of the mechanism for SN2 is called backside attack. I wrote it because it was worth writing. When you think of SN2, the first thing I want to come to your mind is backside attack. Most important thing. And in fact, we'll use that kind of idea to kind of determine some of the different substrate effects and nucleophile effects and things of this sort that are all related to SN2 reactions. So keep that in mind. We'll talk a little bit more about what that means in a second, but first and foremost, that's the first thing I want to pop in your mind when you think of an SN2 reaction. All right, so here we've got sodium cyanide. You should realize that sodium's a metal, carbon's a non-metal, and so that's an ionic bond. So being an ionic bond, whether they write it or not, we should have positive and negative charges. So here we've got a sodium cation and the cyanide anion. And we'll find out that having an anion for your nucleophile, so it turns out cyanide here is our nucleophile. So, and having an anion for a nucleophile generally means it's going to be a strong nucleophile. So, and what's going to happen here is that cyanide here is going to do nucleophilic attack, and it's the backside attack. The nucleophile is doing backside attack, and what we mean by backside attack is that it's attacking 180 degrees opposite from where the leaving group is leaving. So here, 180 degrees opposite from where that bromine's going away. We'll talk a little more about that in a bit here. So, but when we attack there, so that carbon's already got a filled octet, and already having a filled octet, if we're going to make a new bond, so when we say nucleophilic attack, you should think nucleophilic attach. So we're attaching a new bond here. Well, this carbon's already got 4 bonds. There's a hydrogen not shown. So if we're going to make a new bond, we have to have an old one leave. And that's why our leaving group here is going to break off and leave. Now we'll find out that one of the products of our backside attack is what we call inversion of configuration. And so in this case, showing inversion is a little bit of a problematic thing here. So, but one of the things we can do is, oftentimes we'll draw it in such a way that your leaving group's either on the wedge or the dash, and then just attach your nucleophile in the opposite position. It's kind of one of the easiest ways to kind of represent inversion, although it's not a very literal way of looking at what inversion actually is. So, but we'll keep that in mind. All right, so in this case, again, if we look at our rate law, the nucleophile shows up here in our rate law. And so whether we wanted to call that, sodium cyanide or just plain cyanide, I'll put the entire thing. So you could just put cyanide there. And then our substrate, which in this case is the 2-bromobutane. And there's our rate law. And so some typical questions you might get. So first one is, what would happen to the rate of this reaction if you doubled the concentration of sodium cyanide? Well, here I can see that the rate is directly proportional to the concentration of sodium cyanide. So if you double the concentration of sodium cyanide, you double the rate. Second question, what would happen if I double the concentration of 2-bromobutane? And once again, the rate's directly proportional to the concentration of your substrate. So if you double the concentration of 2-bromobutane, you'll double the rate. Finally, you get what happens to the rate if you double both concentrations. And so if we double the concentration of sodium cyanide and double the concentration of 2-bromobutane here, then the rate's going to go up by a factor of 4, because 2 times 2 is 4. Doubling, 2 times 2, quadrupling for that rate. Cool, now acetone is our solvent here, and the tricky question you might get in regard to this rate law is, what would happen if I just doubled the amount of acetone used, but kept the number of moles of sodium cyanide and 2-bromobutane the same, constant? Cool, and it looks like, well, acetone doesn't show up in the rate law, Chad, so obviously it's not going to have an effect. And that's the tricky answer that is wrong. So in this case, these brackets mean concentration. It's moles of each of these species divided by the liters of solution. And if you just doubled the amount of solvent, but kept the number of moles of these constant, you just cut their volumes in half. You just diluted them in half. And so in this case, if we double the amount of solvent, acetone, but leave the number of moles of sodium cyanide and 2-bromobutane constant, their concentrations are both cut in half, and a half times a half, the rate would now be 1/4 of that rate you just had a second ago. So be careful. So if you change the amount of solvent, but keep the moles of the other reactants the same, it actually is going to impact your rate law. Okay, so I want to take a little bit closer look at backside attack for just a minute. So if we take a look at this from a different perspective here, so we're going to take a look at bromine right here, and then we're going to have 3 different groups attached like so. So backside attack in this regard has cyanide coming right in between these 3 groups. So right in between those 3 groups, and that's going to cause bromine to break off and leave. Now, cool. So first off, cyanide's job, he has to squeeze in between these 3 groups. And notice these are kind of like the 3 legs of a tripod, and he's got to squeeze in there. And if he does, he's going to form a new bond to that carbon, but to keep being sp3 hybridized and tetrahedral in shape, so these 3 groups have to kind of flip to the other side. And so what we'd end up with as a product so it would be this, and these 3 groups kind of just flip off to the other side after bromide leaves. So you might think of an umbrella flipping inside out is what's really happening. Now this is kind of a pain in the butt to represent and stuff like this. So again, what we normally do to represent this inversion taking place is, again, if your leaving group leaves from the wedge, we'll just replace the new nucleophile there as a dash, or vice versa. That's kind of the easiest way, rather than trying to reflect the fact that there's this inversion and you kind of have this umbrella flipped inside out and things of this sort. So that's a pain in the butt. One other thing you should know, though, is that sometimes you represent the transition state. And that double dagger there means transition state. So in fact, I'm probably going to need a little more room for this transition state. And so in this case, we're forming a new bond from cyanide to this central carbon right here. So we've got the old bond to bromine breaking. We've got this bond right here. And then we've got the wedge and the dash bond. And so for just a brief minute, so the reactant here is tetrahedral. The product is also going to be tetrahedral, but in the transition state, the relationship of these three groups right here, again, these three groups right here, for just a brief instant, they are trigonal planar and 120 degrees apart. So again, they're going to start off all 109.5 degrees apart, and in the final product, they're going to all be 109.5 degree apart, but inverted. But in the transition state, it's trigonal planar. The angles between these three are all 120 degrees, and that's a good characteristic that you should know for an SN2 reaction. That transition state is trigonal planar. Reactants tetrahedral, products tetrahedral, sp3 hybridized in both cases, but the transition state, not the intermediate, but the transition state is trigonal planar. All right, one other thing I should mention real quick. So we've got two different major mechanistic steps occurring here. So the one in red here represents nucleophilic attack. The one in, one in blue here represents nucleophilic attack. The one in red, the leaving group leaving. And because they both happen at the same time, so two different mechanistic steps occurring all at the same time, we say that the mechanism here is concerted. All happening at the same time. That's all that word means, concerted. So for SN2, it's concerted, and the reason that's so important is we'll find out that for SN1, these will happen in two different steps, and it won't be a concerted mechanism. But in SN2 reaction, the mechanism is concerted, and this all happens in a single step. And so if we take a look here, so I'm plot the energy versus kind of the reaction progress, or the reaction coordinate, some people will say. So you'll find that this all occurs in a single step. And so in this case with a single hill, I should say. And I'm not too concerned if you recognize that this should be an exothermic reaction or anything like that at this point, but you should recognize that one step, one hill. That's it. Cool. All right, so let's take a look at some substrate effects for just a second. And let's take a look at this guy one more time, a little bit bigger. So again, we've got our nucleophile. In this case, I'll just generically write nucleophile. And he's got to squeeze in to do backside attack. Now, he's got to fit in between these three atoms right here. And the bigger he is, the harder time he's going to have. And so it turns out how strong a nucleophile is definitely related to its own size. Smaller nucleophiles tend to be have a little more easier time squeezing in here. Bulkier ones, a little harder time. Now, polarizability plays a result as well. So it turns out if a nucleophile is polarizable, like if it can, kind of squeeze and change the shape of its electron cloud, it can also have an easier time squeezing in here as well. So, but right now I just want to really focus on bulkiness. So if you got something fairly bulky, so probably not going to be the greatest nucleophile in the world. Cool. Also, your substrate's going to play a role here because how big the three groups attached in these three locations are also plays a role. The bigger they are, the slower this SN2 reaction is going to go. The smaller they are, the faster it's going to go. And so if we take a look, what could these three things be? Well, the best we could have for an SN2 reaction is that they're all three going to be hydrogens. This is just simply methyl bromide. So that's the smallest atoms you could have attached here. So, and in this case, for an SN2 reaction, that's the best kind of substrate you can have. So if we take a look at substrate effects here for a minute, so we say that methyl halides are the most reactive. Methyl halides the most reactive. Now, if we take and replace one of these hydrogens with some sort of carbon chain, whether it be a methyl, an ethyl, propyl, it's not the most important thing, but any one of those. So let's say I take this top one and I now make it a methyl group. Well, all of a sudden now this is not just simply methyl bromide, but it is now a primary alkyl bromide. So the carbon attached to the bromine, often called the alpha carbon, where the functional group is, in this case the alkyl halide, that alpha carbon is now a primary carbon. So with a primary carbon right there, it actually is still pretty darn fast. Most nucleophiles can still have an easy time squeezing in here to do backside attack. And so primary halide is still really reactive in SN2 reactions. Not as fast as methyl, but still pretty darn fast. Cool, now let's replace yet another one of these with another carbon chain, and it could be a methyl, an ethyl, propyl, whatever. But now this alpha carbon is no longer primary, it's secondary. And it turns out that this actually is going to slow down the reaction significantly. Most secondary halides react in SN2 reactions pretty slowly. They still react, but it's much slower than our primary halides. Cool. And then finally, if you change this last hydrogen for any kind of carbon chain, again, another methyl, for example, all of a sudden now we have a tertiary halide. And it turns out for a tertiary halide, the reaction's so slow that we really kind of just say it's non-existent. Whether or not that is really just so slow, but for the most part, you're just going to treat it in your class as that it is non-existent, that this doesn't react. Tertiary halides don't do SN2. We like to say that backside attack is completely blocked. There's no nucleophiles that can now fit in to do backside attack. So these are our substrate effects. So methyl halides are the most reactive, then primary, then secondary, and then tertiaries don't work. Cool, and as long as you remember that we're doing backside attack for SN2, then you want the least amount of steric hindrance on your substrate possible. And that again is going to happen for methyl, then primary, then secondary. Now, one other thing you should be aware of when it comes to substrate effects. Cool, so let's say I want to do backside attack on either one of these. Well, they're identical right now. So right now they are both, if we look at that alpha carbon right there, primary. And obviously it's the same molecule, so it shouldn't make a difference. But if I go off to that beta carbon now, so oftentimes we give Greek letters and where the functional group is, in this case the alkyl halide, that's the alpha carbon, and then you just go beta, gamma, delta, so on and so forth. And so in this case, if we take a look at those beta carbons, it turns out they can have an impact on how fast SN2 happens as well, but to a lesser degree most of the time. So most of the time we're just going to examine the alpha carbon and just kind of go methyl's the fastest, then primary, then secondary, tertiaries don't react. However, if you do have to compare two different primary alkyl halides, well then the difference might actually end up coming to that beta carbon. And if we look here the beta carbon is a secondary carbon. Here that beta carbon is a quaternary carbon. And it turns out this one right here, even though it's a primary alkyl halide, we said before that primaries actually react pretty fast. Well, this one doesn't. It turns out we call this beta blocking, or beta branching is probably a more proper term, but you'll hear both. So in this beta branching, the more substituted that beta carbon is, the slower it goes as well. And so again, this is of secondary importance here. So that alpha carbon is the most important thing by far. But every once in a while, you get a question like this thrown in there, where the only difference really comes down to the beta carbon on the substrate. Which one's more substituted? This one. Then it's going to be slower, and this one faster. In fact, this is so slow, it's kind of comparable to tertiaries, it turns out. Not something you're necessarily supposed to know, but again, you should know this principle of beta branching. Much less commonly tested upon, but does show up every once in a while. All right, now that we've talked about substrate effects, next thing on the list is talk about nucleophile effects. So it turns out your nucleophile is in your rate law. It is reacting in the only step of typically most SN2 reactions, which makes it the rate determining step. And it turns out, therefore, you need a strong nucleophile. And so the question then becomes, well, how do I recognize what a strong nucleophile is? So, well, one major thing is most of the time your strong nucleophiles are going to have a negative charge. They're going to be anions. So if we kind of got a list over here of all your strong nucleophiles, we got cyanide, azide, chloride, bromide, iodide. So couple with sulfur with a negative charge, couple with oxygen with a negative charge. So, but there are a handful. So it turns out sulfur is an amazing nucleophile, and even when it doesn't have a negative charge, when it's neutral, it's still an amazing nucleophile, it turns out. Not as good as when it has a negative charge, but still considered a strong nucleophile. Also, nitrogen and phosphorus, also strong nucleophiles, or at least moderately strong, with no negative charge when they're neutral as well. So, but most of the time, though, you're not going to see these all that often with the sulfurs, the phosphorus, the nitrogen with no negative charge. Most of the time, the strong nucleophiles you're going to see in this chapter are going to have a negative charge. And you're going to find out that's going to be the key hallmark. All of your weak nucleophiles, we'll find out and talk about later on in this chapter, are going to have no negative charge. They're going to be neutral. And so this will be one of the major determining factors we'll find out later. So it turns out a couple things we should realize. We'll get into solvents here a little bit at the same time. There's two major types of solvents we're going to use in this section. We call them polar protic solvents and polar aprotic solvents. Now, non-polar solvents, we're pretty much not going to use in this section, so I'll leave them out. And so when I write protic solvents and aprotic solvents, know that I'm referring to them as being polar in both cases. Now, protic refers to a solvent that is capable of hydrogen bonding. So, and water and alcohols are the most common by far. And it turns out when we talk about protic solvents versus aprotic solvents aren't capable of hydrogen bonding, that how strong nucleophiles are changes. Now, it turns out that protic solvents solvate ions very well. They form stronger ion-dipole interactions with ions. And so in this case, if you were going to dissolve, salt in a liquid, would you rather try and dissolve salt in water or salt in oil? Well, you'd choose water. So because water is polar, and it's not just polar, it's protic, which kind of I like to think of means superpolar. And the ion-dipole interactions it forms with the ions is much stronger, and therefore they're much likely to dissolve to form those ions. Whereas if you put salt in like oil, well, that's just going to sink to the bottom or float on the top depending on the salt, and it's not really going to dissolve to any significant extent because you're not forming ion-dipole interactions with nonpolar molecules. Cool. So we got polar protic, polar aprotic, and if you want to solvate ions, polar protic is your solvent. Problem though is that I need a strong nucleophile. Most strong nucleophiles have a negative charge, which means they're going to get solvated more by protic solvents. And what that means is they're going to form stronger ion-dipole interactions, which is going to lower their energy. And so this protic solvents actually stabilize nucleophiles, making them less reactive. And so if I need a strong nucleophile for an SN2 reaction, then I'm going to do better if I do the reaction in an aprotic solvent. Cool. Now, if we look at aprotic solvents first, it turns out that nucleophile strength is going to increase as you get less electronegative. So it turns out, having a negative charge, let's say, so if you're more electronegative, you're more stable having the negative charge, which makes you less reactive as a nucleophile. So less electronegative nucleophiles are more reactive. Well, that is never going to change, whether you're in a protic or an aprotic solvent. So less electronegative, as long as you're comparing, atoms in the same group, they're going to be the stronger nucleophiles. So, however, we're going to see the vertical trend here related to size is going to change. Now, in an aprotic solvent, nucleophiles generally get stronger as you go up a group. Cool, and the idea is just that smaller nucleophile, in fact, this just follows the same as the base trend. Bases get stronger as they get smaller and as they get less electronegative as well. So exactly the same as the base trend. And you might think of a nucleophile as kind of analogous to a Lewis base, so not surprising that it follows the same trend. What is surprising, though, is that when you go to protic solvents, the vertical part of this trend related to size changes. So, and it turns out in protic solvents, it turns out all nucleophiles get weaker. All negatively charged nucleophiles anyways get weaker. So however, the smallest nucleophiles, like these in period 2 here, they form the strongest ion-dipole interactions with, say, water or an alcohol or any kind of protic solvent. And so they are stabilized the most. And so it turns out the big ions, they form much weaker ion-dipole interactions, and so they're stabilized less. They're lowered in reactivity less. And so all of a sudden, when you go to protic solvents, the small ones see a huge decrease in reactivity, whereas the large nucleophiles see only a small decrease in reactivity, so much so that the vertical part of this trend is now different. And so in this case, it turns out that larger nucleophiles are stronger when the solvent is protic. Cool. Part of this is due to polarizability as well, but I'm not going to get into that too much. But larger ions are more polarizable as well. All right, so now we kind of got into distinguishing these trends with nucleophiles and solvents and stuff like this. And the reason that's important is you might, a lot of the questions in this chapter are going to be like comparing rates. And you might, have two reactions that are, exactly the same in every respect except which nucleophiles involved. And so you got to be able to compare nucleophiles, who's stronger, who's weaker, with one of these two trends. And again, most of the time for SN2, we'll see that we'll use aprotic solvents. And it turns out if you've got, carbon, nitrogen, oxygen, or fluorine nucleophiles, you pretty much got to use an aprotic solvent. However, for some of the bigger nucleophiles, you can get away, so period 3 and below, you can get away with using protic solvents. It would still be faster in an aprotic solvent, but you can get away with it at least using protic solvents. But for the small period 2 nucleophiles, you pretty much got to use your aprotic solvent instead. All right, so here I got this big list of our strong nucleophiles. So, and this is going to be one of the hallmarks of how we recognize whether or not we're doing SN1 or SN2, as we'll see later on when we compare this to SN1 reactions. Okay, so let's take a look at those solvents a little bit more closely here. And typical protic solvents are going to be water, any kind of alcohol, or in some cases, carboxylic acids, though less common. But most of the time, it's water and alcohols for protic solvents that we'll see in this section. Whereas aprotic solvents, again, ones that are not capable of hydrogen bonding. So in many classes, you got to not only know the identities of a variety of aprotic solvents, but you got to know their structures as well. So in this case, the four most common polar aprotic solvents are acetone, dimethyl sulfoxide, aka DMSO, acetonitrile here, and then dimethyl formamide, aka DMF. Cool, and these are the four most common. So you might also see like diethyl ether or THF, tetrahydrofuran, or HMPA is a little less common, but those are others that show up in different textbooks with different professors. But these four are fairly universal. These are the four most common polar aprotic solvents. Well worth your time to memorize these. Cool. Most of the time, again, you're going to see these. It's going to be associated with an SN2 reaction because SN2 reactions work better in polar aprotic solvents. And I say better, I mean faster in polar aprotic solvents. All right, last but not least, we got to talk about leaving groups, and the better the leaving group, the faster the reaction. So you'll find out that as far as the halides go, iodide is your best leaving group. Then, well, let's not skip bromide here. Then bromide, then chloride. And the idea is that iodide's a weaker base than bromide, and bromide's a weaker base than chloride. And again, you might remember this from Gen Chem, where HI was a stronger acid than HBr, and HBr was a stronger acid than HCl. If HI is the strongest of those acids, then I- must be the weakest conjugate base. So, or you might just remember it from the trends that we learned just a second ago as well, and that larger bases are weaker bases. All right, so as far as the halides go, these are your good leaving groups. It turns out once you get to fluoride, HF is not a strong acid, and F- really is a weak base, and it's not a very good leaving group. But these are all considered good leaving groups. Iodide's the best, though. So, and a couple others you might see, something abbreviated OTS, that's called a tosylate ester. So, and there's a couple different tosylate esters, but he's the most common by far. And if you kind of take a look at what his structure looks like here, so it looks like this. So, and he's a super weak base, because in this case, the negative charge on oxygen, usually we associate a negative charge on oxygen as being a strong base, like on hydroxide, but not in this case, because it's stabilized with resonance. This negative charge is shared between all three of these oxygens. And so this guy's a fairly weak base, and you should recognize a structure like this as a good leaving group. Cool. Sometimes they'll just kind of generically write this with an R right here, because sometimes it's just a methyl group or a trifluoromethyl group or things of this sort. But again, this one is what we abbreviate as OTS, which stands for a tosylate ester here instead. Cool. And sometimes they're just going to give you a leaving group you've never seen before. And the thing they're looking for you to recognize is that, can you show that it's very stable and therefore a weak base and a good leaving group? Cool. But these are the most common leaving groups. One other thing to note, if you look at starting a substitution reaction with an alcohol, so not as your solvent in this case, but I'm saying, what if this guy were your substrate? Well, he wouldn't be a very good substrate for a substitution reaction here, because OH, if he leaves, is a very strong base. That's hydroxide. It's kind of like our standard Gen Chem definition of a strong base. So he would not be a good leaving group at all. And so finds out if you start with an alcohol instead of like an alkyl halide, so then one of the ways you can kind of convert this into a good leaving group is by protonating it. And so if you use something like, say some sulfuric acid or something, some strong acid, you can protonate that alcohol. And so now, instead of trying to have this leave as hydroxide, which is, again, not a good leaving group, now it's going to leave as water, which is a weak base, and therefore a good leaving group. And so we'll find out that with alcohols, this is kind of a special case for substitution reactions. So is that in acid, they might do substitution. Without the acid here, substitution is not normally going to happen. So when we get to the alcohol chapter in second semester, you might see some examples of this and stuff like this. But for now, so suffice to say, you have to treat alcohols kind of as a special case. They've got to get protonated before this can leave. And then we'd add something else in here to be the nucleophile. And we'll find out we're pretty limited on what we might use for nucleophiles in a highly acidic solution here. So, but alcohols have to get protonated to turn the OH into a good leaving group, and here again, leaving as water. All right, so now let's take a look at SN1 reactions. And just like with an SN2 reaction, the first thing I wanted to come to your mind was backside attack. With an SN1 reaction, we'll find out that the major and most important intermediate in the reaction is a carbocation. And so the first thing I want to come to your mind for an SN1 reaction is carbocation. So in fact, I want it to come to your mind so much that I wrote you a horrible song. So when the song goes, SN2 backside attacking you, SN1 carbocation. Yeah, it's horrible. So, and if you're sleeping tonight and you're thinking of that song, I am sorry. And one, you got problems. You probably don't get out too much. Well, in fact, we all don't get out too much right now. So, but that's the song. SN2, backside attacking you. It's all about backside attack. And then SN1, carbocation, because it's going to be all about the carbocation. And again, these things are important because they remind us of the different substrate nucleophile effects that'll be involved in stuff like this. So SN1, we call it substitution, nucleophilic unimolecular. So, and again, whereas SN2 is bimolecular, this is unimolecular. Only one reactant molecule involved in the rate determining step. And it turns out that reactant molecule is going to be the substrate. Only the substrate's involved as a reactant at slow step. And it's first order. So, and that's what the unimolecular means. Only one reactant molecule and a first order rate law. So in this case, if we come and take a look at that mechanism, it turns out in step 1, your leaving group leaves all on its own. The nucleophile is not involved in this whatsoever. And if that leaving group leaves, that's where our carbocation intermediate comes from. Cool. Carbocation here. So notice that word. It's not a carbocation. It's not like you're taking a vacation from carbohydrates or something like that, like the Atkins diet. So it's carbocation. So, and your carbocation here does not have a Phil octet. Positive formal charge, typically highly unstable, so super high energy intermediate. So this first step is going to be very endothermic, big uphill increase in energy. So, and this is going to be the slow step in your reaction, the rate determining step, we often say. Cool, and because only our substrate here, in this case 2-bromobutane is involved, that's why he's the only one showing up in the rate law. So if we write the specific rate law in this case, cool, there's your 2-bromobutane. Cool, you double his concentration, the rate doubles. Done. That's all you want to know about this guy here. Now, this gets a little bit tricky here because then who is our nucleophile? Well, that nucleophile here is methanol. Now, it turns out methanol is a weak nucleophile. He does not have a negative charge. He's just an alcohol. A lot of students see this and they're like, hey, Chad, he's got an OH, Chad. Look, he's got an OH. He's not a metal hydroxide, which is ionic. And that has a metal hydroxide. Hydroxide's a strong nucleophile. But that's a non-metal. He's bonded to carbon. This is just an alcohol. This thing is about as reactive as water. Water's not a good nucleophile, not a good base. He's not a good nucleophile, not a good base. So in this case, weak nucleophile, but your carbocation is so highly reactive, he doesn't care. He's like, I just need somebody, anybody. So your next step is nucleophilic attack. Cool, and oxygen's going to come and attach to that carbon right there. Cool. Now, one thing you should note is how we attach that carbon's a little bit unique here. So this carbon right now is no longer tetrahedral and sp3 hybridized. Once the bromine leaves, he's now sp2 hybridized. That makes him trigonoplanar and flat. He exists in a single plane here. And so when methanol attacks, he either attacks from the front face or the back face. If he attacks from the front, it would be a wedged bond. If he attacks from the back, it would be a dashed bond. And so in this case, what I might do, instead of drawing them both out, is I might just make it a squiggly bond. One possible convention. Or I could take the time to draw both wedged and dashed versions of this intermediate out, but that's kind of lengthy for drawing intermediates. For drawing the product, we'll do it, but not for an intermediate. Cool. Now, one big difference here is our nucleophile here was not negatively charged. He's neutral. Notice you look at oxygen here. Oxygen's bonded to carbon and to a hydrogen. He's got 2 bonds, and we're used to seeing oxygen have 2 bonds like in water and stuff. So he normally has 2 bonds. Well, all of a sudden now he's got 3 bonds. And when you've got a neutral nucleophile, it ends up having 1 additional bond past what it normally likes to have, if one will use that. Whereas when you start with a negatively charged nucleophile like we do in most SN2 reactions, it's already short a bond, and making another bond gives it its normal number. So in this case, this thing, you might recognize oxygen with 3 bonds at a positive charge, very analogous to H3O+, which is a strong acid, and this thing's highly acidic as well. And if you get here, as long as you have an H, you're going to let your solvent come and deprotonate, do a proton transfer reaction. So in this case, it turns out methanol is not just the nucleophile, he's also the solvent. And being the solvent, we'll have another molecule come in. Our solution is chock full of solvent molecules, so if I need to use one, I'll just draw it in. And we'll come and deprotonate here. And again, generically called a proton transfer. And now I'll take the time to draw out both versions of this. Cool. So we get, in this case, since this happened at a chiral center, we get both the R and the S forms here, so both enantiomers, if you will. Cool, so that's one big distinguishing factor between SN1 and SN2. With SN2, we only saw inversion. For SN1 here, though, if it happens at a chiral center, we say that racemization takes place, even though we'll find out this is not a true racemic mixture. So, and then also we get one of our solvent molecules protonated as well, though we wouldn't, normally look at him as being a product, although if I'm drawing out the mechanism, I should draw him in. Cool, but if I'm just, drawing organic products, we would just draw these two. Again, not part of a mechanism, just said if we're just predicting products. Yep, draw these two. Cool. Now, like I said, this is not a true racemic mixture because it's not exactly 50-50, it turns out. So it turns out we're going to get a slight excess of the inverted product. So in that case, that's this one down here. So a little higher than 50%. And of the retained stereochemistry, we're going to get a little lower than 50%. So it turns out that bromine here is leaving from the wedged position. He's leaving from the front side. He's like, I'm bromine and I'm big, and I'm leaving from the front side. And as he leaves, he blocks the way from methanol attacking from the front side. Now again, methanol, bromine leaving and methanol attacking is two different steps. So, and even though they're isolated in time, bromine's still out here in the way a little bit out in front of the molecule, having left from the wedge. And so methanol has a harder time attacking from the front than the back. So, and again, it's, it's not like it's 90-10 or anything like this. So in this case, we don't want to define it anything more than saying a little higher than 50%, a little lower than 50%, but it's not a true racemic mixture. And you should know that the inverted product, there's a slight excess of him. So, but again, we still say that racemization takes place in an SN1 reaction. All right, one other thing to note, another big buzzword. So for a lot of SN1 reactions, it doesn't have to work out this way, but it usually does. So is that your solvent and your nucleophile are one and the same. So, and when your solvent's involved in a reaction as a reactant, your solvent's getting consumed in that reaction, and we will call it a solvolysis reaction. Cool. And so there are a lot of solvolysis reactions that exist. SN1s, a lot of SN1s are just examples of solvolysis, but SN2s typically, and I can't actually think of an exception, are not solvolysis reactions. So if I say the word solvolysis in this context, you think SN1. Now, we'll find out, towards the end of second semester, there's a lot of other reactions that end up using the solvent as part of the reaction that could be termed solvolysis. So I don't want to use this universally, but in this chapter, if I say solvolysis, you should think, oh, that means SN1 reactions in this chapter, not SN2. All right, so another big buzzword to take away here. So if we take a look at some of the substrate effects now, so again, SN1 is all about the carbocation. So and somewhere along the way, you guys learned that tertiary carbocations are more stable than secondary carbocations, are more stable than primary carbocations, are more stable than methyl carbocations. And so as a result, we'll find out that tertiary halides react the fastest, then secondary halides. So, and then finally primary halides and methyl halides, the carbocations that result from primary methyl halides are usually so unstable that they're just not going to form. And so tertiary halides react the fastest, then secondary, and then primary methyls we say don't react in SN1 reactions. Now there are exceptions. If it's a primary halide and it's allylic, if there's resonance, so potential for the carbocation, well, that would be an exception. So, but that's not kind of part of this normal trend. But so if I gave you something like this, so this is not just primary, although he is primary. So, but he's primary and again, what we call allylic. And if this chlorine were to up and leave, we'd get this resonance stabilized carbocation, and we could draw that other resonance structure. Cool. But outside of any kind of resonance stabilization to your carbocation, tertiaries react the fastest, then secondaries, primary methyls don't react, again, barring some sort of resonance. Cool, but we should keep in mind that resonance can stabilize our carbocations as well. It's not just about most substituted, although that's what it's about most of the time, but resonance stabilization can also play a role for SN1. All right, so now we see this is the exact opposite trend as we saw for SN2. For SN2, which was all about backside attack, we wanted the least amount of steric hindrance possible. And so methyls were the fastest, then primary, then secondary, tertiaries don't react. Now it's tertiaries that react with actis because we're getting the most stable carbocation, then secondaries, and then primary and methyl halides don't react instead. Cool, and those are our substrate effects. Cool, one other thing you should look at. So if we look at first the energy diagram for this reaction, the one we did right here, and in case you're wondering, RxN is my shorthand for reaction. So we'll plot energy versus reaction progress. We can see that we got 1 step, 2 steps, 3 steps. And so SN1 reactions, again, they don't have a concerted mechanism. So the leaving group leaving and the nucleophile attacking is in 2 different steps. And so you're always going to have more than 1 step. You're going to have at least 2, and in this one we see we have 3, which is pretty common. 3 steps is going to mean 3 hills. So, and in this case, you'll find out that that first step, it's going to have the highest activation energy because we're forming that very high energy carbocation intermediate. That's going to be the slow step. It's going to have the highest activation energy. Cool. And if we kind of take this the rest of the way. And so in this case, again, 3-step reaction gives me 3 hills. And the first step definitely had the highest activation energy out of any of those 3 steps. So, and that would be another way of recognizing its slow step, if you will. So if we look at an energy profile here, it's definitely easy to distinguish SN1 from SN2. SN2 reactions, again, typically have just a single step, concerted mechanism. SN1 reactions are always going to have at least 2 steps, but 3 here is pretty common, with that last proton transfer step being really common for a lot of SN1 reactions. All right, so again, the kinetics are all about forming that carbocation in that first step. And one way we can kind of facilitate this, it turns out, is by adding some silver nitrate into our solution. So we often use silver nitrate to help SN1 reactions happen. And specifically when we have chloride, bromide, or iodide as our leaving group. So it turns out that once bromide leaves here, once we've done that first step, and we get here, so notice he can go forward, but also there's not a huge activation energy to go backward as well. He might decide, I'm just going to go back and reattach. That was a good place to be. So, and in this case, to prevent that, we can add some silver nitrate. And the idea is that silver halides are super insoluble. Silver chloride, silver bromide, silver iodide. And so as soon as bromine leaves, so our silver ions here are going to combine with that bromide and precipitate out. And either we draw, a little S for solid, or oftentimes we'll draw that little down arrow, which means it precipitates and falls out of the solution. So because the bromide's now part of a precipitate that fell out of the solution, this becomes irreversible. And so this helps aid in carbocation formation. So if you see ever, not just methanol or water or something like that, some weak nucleophile we'll find out, but silver nitrate written as well, you should think, oh, they're trying to aid in carbocation formation. We'll probably do an SN1 there as well. So just wanted to throw in silver nitrate's not, going to be part of the product or anything like that. It's just there to aid in carbocation formation. Cool, let's also talk about nucleophile effects for just a second. So with SN2, the nucleophile was in the rate law, it was in the rate determining step, and we needed a strong nucleophile. But in SN1 reactions, it's not in our rate law at all. It's not part of the rate determining step. So, and we're going to find out that weak nucleophiles are okay. In fact, most SN1 reactions involve a weak nucleophile. If they involved a strong nucleophile, they'd probably do SN2 instead. So most weak nucleophiles, most SN1 reactions, your weak nucleophile is going to be the case. And the idea is that your carbocation is a super reactive electrophile, super unstable, high energy electrophile. And he's like, I don't need a strong nucleophile. Just any nucleophile will do. Let me bond to a nucleophile. Perfect. Methanol, water, you're ugly. Great, I don't care. That works. So that's kind of the idea here. Weak nucleophiles are okay for SN1 reactions, and that's going to be the case most of the time. So we'll find out that SN2s, we need a strong nucleophile. SN1 reactions, most of the time, are going to involve a weak nucleophile, and that is probably the single biggest determining factor between SN1 and SN2 is the strength of the nucleophile. If you can recognize that you have a strong versus a weak nucleophile, you've probably just figured out whether or not you're doing SN2 versus SN1. Cool. Second after that will be the substrate effects. Notice here, if you've got a tertiary substrate, you're doing SN1, not SN2, because SN2 can't use tertiary substrates. If you've got a primary or methyl substrate, well, then you're probably doing SN2 because you can't use primary methyl substrates in SN1, again, barring any sort of resonance, stabilization of your carbocation. So keep that in mind. One other pesky thing we got to talk about here with these carbocations. So in somewhere in the course, you probably learned that carbocations can undergo rearrangements. This is not something we ever had to worry about with SN2. We don't even have an intermediate in SN2 reactions. So, but for SN1 with a carbocation intermediate, we do sometimes have to worry about carbocation rearrangements. Now in the example we did up here, we didn't have to worry about it. Our carbocation was secondary. Typically the rearrangements can only happen to one of the adjacent carbons and only if the carbocation gets more stable. Well, going from secondary here, I've got an option to go to a primary here or to another secondary here. That's not more stable, and equally stable is not good enough. It has to be a more stable carbocation as it rearranges. So there's no favorable rearrangement here, so it wasn't something we had to worry about. But let's do an example where we do have to worry about rearrangements. All right, so let's take a look at this next reaction here. So we have got a secondary halide on our substrate, or for our substrate anyways. And again, methanol, an alcohol, another weak nucleophile, just like we saw before. We should be predicting SN1. So first thing that's going to happen is your leaving group is going to leave, and we're going to form that carbocation. Cool. And in this case, having a secondary halide as our reactant, we've now formed a secondary carbocation. So a secondary carbocation has two adjacent carbons, these two right here. And the top one here is secondary, but the bottom one is tertiary. And so we do have a favorable rearrangement. We can get a more substituted, more stable carbocation right next door. And we would accomplish that with a hydride shift. And so I'm going to draw in the hydrogen that's going to move over here. That hydrogen, the bond's going to break and reattach over here. That's going to leave what was formerly our carbocation, so having a filled octet now, and now this carbon will be missing a bond and be the carbocation in the subsequent structure. All right, notice I didn't draw the hydrogen in on the adjacent carbon or anything like that. We often don't draw hydrogens in unless they're part of the mechanism. So it's there. That guy now is a filled octet. So, but this carbon here is now missing a bond. He's only got 3 bonds. There's no hydrogen there anymore. So, and having only 3 bonds, he's not sp3 hybridized and not tetrahedral. He's now sp2 hybridized and trigonal planar and flat. And that's why I've not drawn this as a wedge, because he's not a wedge. This is now trigonal planar, not tetrahedral. All right, now it's a tertiary carbocation here, and again, most of the time when rearrangements occur for carbocations, typically there's one favorable rearrangement. But there's nothing to say that it can't have more than one successive rearrangements, but it does have to get more stable every step along the way. And so we should just verify that none of the adjacent carbons here would be more stable. So with our tertiary carbocation, it's next to a secondary carbon here, not more stable, next to a secondary carbon here, not more stable, and next to a primary carbon here, not more stable. So we're done with rearrangements. And so now we can kind of see where methanol would ultimately come and attach to get to the major product. All right, so that's where methanol is going to attach. And eventually, again, one of these H's will get deprotonated like we showed in the mechanism before. So that's why I'm kind of drawing 2 arrows here. We're taking 2 steps, combining them to one, not showing the complete mechanism here. Just wanting to get to this final product. Cool. So again, all of methanol attached right in that location and then got deprotonated by another methanol molecule. So it takes 2 steps to get to this final product. Now, in this case, where we ultimately attach, that is not a chiral center. So it is bonded to 2 identical groups as you go around the ring. And so since there's no 4 different groups there, that's not a chiral center. And if it's not a chiral center, well, then I don't really care about stereochemistry. Whether I'd show the wedges and dashes, it only exists in one way. So whether I make the CH3 the wedge and the OCH3 the dash, or the OCH3 the wedge and the CH3 the dash, it's the same thing either way. So we don't have to show stereochemistry if it's not a chiral center. So we get a single achiral product in this case. And so the idea that inversion takes place in SN2, whereas racemization takes place in SN1, only if the reaction's occurring at a chiral center will we even notice those things. Cool, so not the case here, but we did go through a carbocation rearrangement. And notice not only did we kind of get a rearrangement of the carbon skeleton here, but it also added an additional step to our mechanism. So in this case, we had our first step was carbocation formation, second step was rearrangement of that carbocation, and then 2 more steps to get to our final product for a total of 4 steps in this one. So if you drew out the energy profile, you'd see 4 hills on the way to your product and stuff like that. So mechanism a little longer when you have a favorable carbocation rearrangement. One other thing to note, it doesn't mean that all product is formed through rearrangement. It just means that your major product is formed through rearrangement. So you might see a little bit of this product. It could be a wedge or a dash in this case. That could have a little bit of that product in your solution. So we're not saying that you get none of it, but if you're asked to predict the major product, you're predicting this guy, not the minor product over here. So just one thing to note. Okay, so we've talked about the substrate effects. The more substrated, the faster for SN1. Talked about nucleophile effects, where simply just most SN1 reactions are going to involve a weak nucleophile. That's okay. Not involved in the rate law. So, and now we've got to talk about solvent effects for just a minute as well. So in SN2, we decided that polar protic solvents weren't the greatest thing because they would stabilize the anion nucleophiles, making them weaker nucleophiles. Well, for SN1, we're going to stabilize an ion as well, but the ions we're going to stabilize are the carbocations, and these are not the reactants. These are the intermediates we form in the rate determining step. So for SN2, the ion we stabilize is the reactant in the rate determining step. You stabilize that reactant in the rate determining step, you slow the reaction down. But now we're stabilizing the intermediate, the product of the rate determining step, and if you stabilize that, you speed the reaction up. And so in this case, our ion dipole interactions with polar protic solvents stabilize the carbocation. We're going to form these ion dipole interactions with our carbocation and the leaving group anion. And it turns out without those interactions, these reactions don't go. SN1 reactions have to have polar protic solvents to form those strong ion dipole interactions and stabilize the carbocation. So without polar protic solvents, SN1 reactions don't occur. So there's another distinguishing factor. It's kind of the least important of them. But for SN2 reactions, polar aprotic was strongly preferred. So with bigger nucleophiles, you can get away with using polar protic, but it will still go faster with a polar aprotic solvent. But for SN1, no ifs, ands, or buts. Your solvent has to be polar protic. Can't use polar aprotics at all. And so if your solvent is polar protic, well, it could be SN1 or it could be one of the rare SN2s. Okay, but if your solvent's polar aprotic, well, you can't do SN1 and it has to be SN2. All right, one reminder, your typical polar protic solvents, water, alcohols, and maybe an occasional carboxylic acid, but water and alcohols most of the time. Cool, finally one more thing here and talking about leaving groups. So the leaving group leaves in both SN1 and SN2 reactions. That's the one thing they have in common. In the rate determining step, the leaving group leaves in both. In an SN1 reaction, that's the only thing that happens. In an SN2 reaction, it's one of the 2 things that happens. In an SN2, you have the nucleophile attacking and the leaving group leaving. But in both SN1 and SN2, the leaving group leaves in the rate determining step. And you need a good leaving group in either case. And so the leaving group trend here is exactly the same. So OTS would be better than iodide, iodide would be better than bromide, bromide would be better than chloride, and fluoride would be a bad leaving group again. So we can rank the speed of SN1 reactions. If the only difference is your leaving group, you can use this ranking to figure out who's faster, who's slower as well. Cool, we've kind of covered SN1 and SN2 at length here. So we're gonna do some comparisons between the 2, but there's one other kind of halide we should really talk about. So, and that halide is what I'm gonna call an sp2 halide. So if your halogen's attached to an sp2 hybridized carbon, it turns out you're not doing SN1 or SN2 in that case. So if you've got something like this, or maybe this. So substitution, SN1 and SN2 is not going to happen. So it turns out whether you have what's called a vinyl halide or whether you have what's called an aryl halide, doesn't matter either way. You've got the bromine attached to an sp2 carbon in both cases. So you can't do SN1 first off. So if the leaving group were to up and leave, the carbocation that would result here would actually be less stable than even a primary carbocation, and those don't usually form. So this is really not going to form a carbocation. So no SN1. Also, So backside attack is blocked or repelled, if you will. So the pi electrons actually block access to the backside and repel away your nucleophiles, whether it be on the benzene or on the alkene. And so you're not going to do backside attack either. And so as a result, no SN2. And so no SN1, no SN2 for sp2 halides. Again, get rid of these double bonds and we can do the reactions, or at least consider them. But sp2 halides, completely unreactive. All right, let's take some time to do some examples. All right, if we're going to compare SN1 and SN2, we want to look at the different criteria and see how things play out so we can really distinguish very quickly between the two. So, and once again, we've already covered all these. I just want to summarize them in a table here. So if we look at SN2, for your substrate, you're doing backside attack, you want the least hindered backside attack possible. And so methyl is the most reactive, then primary, secondaries are pretty slow, and tertiaries don't react. Whereas for SN1, you want the best carbocations, the most stable carbocation, tertiary carbocations the most stable, then secondary, and then typically primary and methyl don't react. So we see exactly the opposite kind of relative rates. So versus least substituted versus most substituted for SN2 and SN1. Now, your nucleophile, the nucleophile is involved in your slow step in SN2, and you need a strong nucleophile. The nucleophile is not involved in the slow step or in the rate law, and so we say that a weak nucleophile is okay. It's not that you can't have a strong nucleophile, but most of the time if you've got a strong nucleophile, you're doing SN2. This is the single biggest determining factor of whether you're doing SN1 or SN2. So in fact, I think it's the first thing you should evaluate, but most of the time to figure out and be sure of who your nucleophile is, you probably want to identify your substrate, and your substrate's the one with the leaving group. All right, your solvent. We said that most strong nucleophiles have a negative charge, and polar protic solvents would stabilize that negative ion a lot, slowing the reaction down, so we want polar aprotic, strongly preferred. Whereas for SN1, it's not just strongly preferred, but your solvent has to be polar protic so that it can form those strong ion dipole interactions and stabilize those carbocations. Finally, your leaving group. This is the one thing they have in common. In fact, we can just kind of make a big general trend here. OTS is the best, followed by iodide, followed by bromide, followed by chloride. Exactly the same trend for both SN1 and SN2. Finally, rearrangements. And as long as you're forming a carbocation, rearrangements are possible. I shouldn't say yes, maybe I should say possible. So whereas for SN2, we'll just put no because they are not possible. There's no carbocation intermediate. In fact, there's usually no intermediate at all, so not possible. And then finally, stereoselectivity. So for SN2 reactions, they undergo inversion. And again, you'll only notice this if it happens at a chiral center. Sometimes this is called Walden inversion, in case you're curious. So, and then finally for SN1, you're attacking an sp2 hybridized trigonal planar flat carbocation. And so you can attack it from either side. And so if it happens at a chiral center, racemization will take place instead. Cool. So these are your big differences. This is what you want to keep in mind. And again, your nucleophile is going to be the first and most important indicator of what kind of reaction, which one of these two mechanisms you're using. After that, your substrate, and then your solvent will be of lesser importance after that. Let's take a look at some examples. All right, we're going to start here with some very standard examples, and then we'll do a couple of very, I don't want to say exceptions, but less common examples here at the end. So for our standard examples, so I want us to identify our substrate, identify our nucleophile, and usually by the time we've done that, we'll kind of know which of the two mechanisms here we're doing for substitution. So in this case, leaving group in the first one, who is that leaving group? You should have said chlorine. So in that case, that makes that first reactant our substrate. Cool, and then we want to identify the nucleophile and identify if it's strong or weak. And in this case, it's sodium hydroxide, and you should recognize that sodium hydroxide, sodium a metal, oxygen a nonmetal, that's an ionic bond. And so being that you have ions, you've got plus and minus, and when you've got an anion, that is going to be a strong nucleophile. Cool, and if you had to go so far as to look at your solvent DMF, that's one of your classic four most common polar aprotic solvents. But again, usually you're going to identify whether you're doing SN1 or SN2 before you've ever looked at your solvent. So in this case, first and most important thing is your nucleophile. Our nucleophile is strong, not weak. We are probably doing SN2. We'll confirm that with our substrate. In this case, our substrate is primary. So in being a primary substrate, we can see that we're definitely doing SN2 because SN1 is not available to us. Great. So we thought we're doing SN2, now we know we're doing SN2, and the fact that our solvent is polar aprotic is just kind of icing on the cake, if you will, not something we actually really needed to see to figure this out. And so in this case, we do backside attack. It's occurring at a carbon that is not a chiral center. So I don't have to worry about inversion. Hydroxide's just going to do backside attack and replace that chlorine and put an OH there. If it had occurred at a chiral center, we would have noticed inversion taking place, but no chiral center involved in this example. Cool, there's the first product. So second example, who is the leaving group? And you should have said Br. And so that identifies this as our substrate, which makes the only other thing up here our nucleophile. And in this case, being our nucleophile, there's no negative charge. It's not ionic. Don't look at the OH and think you have a metal hydroxide, an ionic hydroxide. This is just an alcohol. And he is a weak nucleophile. And since it's the only thing written, we kind of imply that he's also our solvent. And this is a solvolysis reaction. So but with that weak nucleophile, we definitely know we're doing SN1 because SN2 reactions have to have a strong nucleophile. Cool. If we look at our substrate as well, we can see that this is a tertiary halide, and that's just kind of icing on the cake here as well. With the tertiary halide, we can do SN1. We didn't even have the possibility of doing SN2. Backside is completely blocked for tertiary halides. Cool. And then finally, with an alcohol being our solvent, it's polar protic as well, which again, just more icing on the cake. We've already identified we're doing SN1. And if you're doing SN1, I highly recommend, rather than just simply replacing this with our nucleophile, you draw out your mechanism just a little bit because carbocations can rearrange. And so in this case, our carbocation in this example is not going to rearrange because it's a tertiary carbocation and the three adjacent carbons are secondary, secondary, and primary. No favorable rearrangements, nothing I have to worry about. So in this case, ethanol is what's doing the substituting. Oxygen's going to come and attack that carbon and attach. But again, with a neutral nucleophile, you got to remember that you'll deprotonate right after. And so in this case, we will end up with this as our product, and with this did not occur at a chiral center. If it did, we'd have to worry about racemization taking place, forming both the R and the S. But in this case, this is not a chiral center. He's not bonded to four different things. These two groups in the ring are identical. All right, moving on to the third example. In this case, who's your leaving group? First question you should ask, and it's bromine yet again, so that makes this our substrate. And I didn't really care to identify him as the substrate so much as I wanted to know that he's not the nucleophile. So the other guy here must be the nucleophile. And once again, being neutral in charge and just an alcohol, he is a weak nucleophile, which means we're probably doing SN1. We'll go back and look at our substrate and see that he's secondary. And if you want to ask a tricky question involving substitution, so we usually will involve secondary substrates because both SN2 and SN1, that's the least reactive in both categories. But it also means that both SN1 and SN2 can react with, can involve secondary halides here. So, and again, that wasn't really going to be our determining factor anyways. It was the fact that we've got a weak nucleophile tells us we're doing SN1, and being that we have a secondary substrate, SN1 is indeed possible. Cool. Also, your alcohol is a polar protic solvent. It's not only the nucleophile, it's the solvent. This is another solvolysis reaction. Again, another way you might identify this as SN1. All right, in SN1 reactions, I highly recommend you draw out your carbocation intermediate just to check for those rearrangements yet again. Cool, in this case, we're going to form that secondary carbocation, and neither of the adjacent carbons is going to be a more stable carbocation. Have a secondary on the left, a primary on the right, nobody more stable than the secondary carbocation we already have, so no favorable rearrangements. That's where methanol is going to attack and attach, and then get deprotonated. And so this is what our product's going to look like. And in this case, we do have to look and say, oh, this does occur at a chiral center. So because it's occurring at a chiral center, we have to remember that SN1 reactions, when you attack a carbocation, you can attack it from either side. And so racemization is going to take place. You're going to get both R and S. Now, there's a couple different ways to represent this. Now, some people will just say, hey, you know what? Don't even show the stereochemistry, just write plus and minus afterwards. That just tells me I get both the plus enantiomer and the minus enantiomer. So some professors don't like that. They're not as favorable to that. So I highly recommend what's always acceptable is just drawing out both enantiomers. you'll always be safe doing it that way. Okay, moving on. In the next example, who is your leaving group? And hopefully you said chlorine. So, and in this case, chlorine is our leaving group. That makes this our substrate. Cool. And your nucleophile, you should realize that sodium is a metal, sulfur is a nonmetal. That's an ionic compound. And having a negative ion, that's a strong nucleophile. In fact, sulfur is pretty much the strongest of the nucleophiles we know. So this is an amazing nucleophile in this case. And finally, if you cared, you could have identified DMSO as a polar aprotic solvent and stuff, but once you knew you had a strong nucleophile, you probably knew that you're doing SN2. So we just got to make sure it's possible. Look at your substrate. Your substrate is secondary halide, and that means SN2 is possible. It's going to be maybe slow, but it is possible. And then DMSO is your polar aprotic solvent, one of the common ones. So everything signals to SN2. But once we identified that we had a strong nucleophile, so greater than 90% chance we're doing SN2 at that point. All right, so we're going to do backside attack. It is occurring at a chiral center this time, and so we do have to remember that inversion is going to take place with SN2. SH is our nucleophile. He's what's going to be replacing that chlorine, but now he'll be a wedge. Cool, and our product is simple as that. All right, finally one more here, standard example. So one, you should look and see, oh, silver nitrate. Chad said something about silver nitrate. Silver nitrate is there to precipitate out the halide and favor carbocation formation, so facilitate carbocation formation. So probably doing SN1 here. So in this case, chlorine is our leaving group, and that makes this our substrate. So, and again, silver nitrate is not part of the product or anything like that. So it is water that is our nucleophile, and being neutral here, it is a weak nucleophile, which means we're doing SN1. So we got a weak nucleophile. Can we do a weak nucleophile here with a secondary halide? Yeah, we totally can. So weak nucleophile, secondary halide, SN1's possible. Water also, again, is our solvent as well and is polar protic. Everything signals SN1. And again, if you're doing SN1, I highly recommend you draw out your carbocation. And in this case, we have a secondary carbocation. So, and if you look at the two adjacent carbons, one's primary, one's secondary, and you say, oh, there's no favorable rearrangements, except that there is in this case. We are actually going to do a hydride shift. So this is a little trickier than the other examples because it doesn't look like there should be a rearrangement, but there is. We'll do a hydride shift. And even though our carbocation didn't get more substituted, the real rule is not that your carbocation has to get more substituted, it's that your carbocation has to get more stable. And in this case, he's not just secondary, he's secondary and benzylic, one bond away from a benzene ring, and he's stabilized by resonance. And so he's not more substituted, but he is more stable, and that's really the rule. Cool, and that is where the substitution is going to take place. Water is going to come and attack. So, but again, with a neutral nucleophile, you'll deprotonate right afterward if possible, and we'll pull off one of the H's, so an OH is going to end up there. That is a chiral center. And so racemization is going to take place. So the OH could be a wedge, or that OH could be a dash. Cool, so little trickier example here, and I'm gonna get trickier still on these last two. So I start off with some really standard ones. We got a little bit tricky with a carbocation rearrangement, and again, a couple of little more tricky ones yet. Let's get some room though. All right, these are our last two examples here. Start with this top one, and my first question for you is, who is your leaving group? And hopefully you said iodide here, and in this case, that makes this first reactant our substrate. Cool, which makes this our nucleophile here, and you should realize this is not an ionic compound, it's just an alcohol, and that makes it a weak nucleophile, which probably means, again, we're doing SN1. If we take a look at our substrate, though, we have a problem, is that this is a primary substrate. And we look at SN1, we're like, we can't use primaries. Unless we said, though, they're stabilized by resonance. And this is not just primary, it's primary and allylic. That is one carbon away from an alkene, and the carbocation we form would be resonance stabilized. And so in this case, we're doing SN1. So weak nucleophiles only have SN1 as an option, and in this case, normally we think primary halides, SN1 would be possible, but in this case it is, because we're going to form this resonance stabilized cation. And once again, I recommend if you form a carbocation, you should draw it out. And in this case, we should draw both resonance structures. It's going to be really important. So in this case, resonance implies that the positive charge here is being shared between two different carbons, not just on a single carbon. And what that means, though, is that our weak nucleophile actually can attack in two different locations. And that's going to be unique to this kind of a situation. So this is doubly tricky. One, it's SN1 with a primary halide because of resonance. But also substitution is going to occur in two different locations because of that resonance stabilized carbocation sharing that positive charge in two locations. So if isopropyl alcohol here attacks on this carbon that shares a positive charge, you get the product that we'd probably expect here. So which is that guy? So just attached isopropyl alcohol to that one and then deprotonated after the fact. Again, with a neutral nucleophile, you typically deprotonate right after. So, but for this other one here, all of a sudden now we form a chiral center in this example. And so you get a pair of enantiomers as well. And so where we substituted in the first example was not a chiral center, no chiral center formation, so we didn't have to worry about racemization. But in the second example, where we substituted here, definitely was a chiral center and led to a racemic pair. Again, not truly racemic mixture, slight excess of the inverted one, or actually in this case it might be truly racemic because that's not where the leaving group left anyways. I actually don't know how that works. But definitely not just the product we might expect, but an additional product here with that positive charge shared in two locations. All right, finally one more example, and my question for you is, who's the leaving group? And hopefully you're saying it is chlorine. Cool, and in this case, you realize that makes this your substrate, which makes this guy your nucleophile. And you should look at him and be like, oh, there's no negative charge. But then some bells might go off in your head and said, oh, Chad said if you have phosphorus, sulfur, or nitrogen, even without a negative charge, they can be strong nucleophiles. And so it turns out this guy still is a strong nucleophile. Even with all the bulkiness going on, it turns out he's still a strong nucleophile. So phosphorus, even neutral, is fairly polarizable and makes a good nucleophile. And he's what's going to be doing backside attack. So in this case, being a strong nucleophile, we should be expecting SN2, strong nucleophile. We've got a primary halide. Again, confirming that we're doing SN2, and there was no solvent even listed here, and sometimes they do that. So, although a good, in fact, actually I did that for a reason. I don't even want to deal with solvent on this one. All right, so we did some backside attack, and we find out then that this is not happening at a chiral center, but we're going to have phosphorus here, and that phosphorus is still going to be bonded to 3 benzene rings. So, and this is where we as organic chemists get lazy. So instead of writing benzene rings, turns out those are called phenyl groups. P-H-E-N-Y-L, not phenol groups, but phenyl groups. And so sometimes we just get lazy. In fact, we're lazy all the time, right? We don't draw carbons. We don't draw hydrogens bonded to carbons. And if we can abbreviate benzene rings, we'll do it. So, and you get this, but that's going to leave phosphorus here also with a positive formal charge. And normally with a neutral nucleophile, like in SN1 reactions, you attack and then you deprotonate it. But phosphorus here doesn't even have a hydrogen to deprotonate. And this actually is your product. We're done. So not the most common thing, which is again one of the things making this tricky. So one, we had a neutral nucleophile that was strong. That was unusual. And also we had a neutral nucleophile that couldn't be deprotonated. And so you end up with a positive formal charge on your final product. Cool. That's the examples I've got for you. And again, I gave you some standard ones, gave you some tricky ones. If you're looking for more examples, again, check out, I got a bunch of practice problems on chadsprep.com as part of my premium course. Hopefully you found this helpful. And again, hopefully the whole reason I made this was a lot of you guys are getting a lot of Zoom lectures right now, or pre-recorded lectures on a tablet and stuff like that. And I know a lot of students made some remarks and wanted to see something on a whiteboard. So gave you a lecture on a whiteboard, and I've got more coming. I'm going to try and make a whole set of lectures for the end of OChem 1, the end of OChem 2, the end of Gen Chem 1, and the end of Gen Chem 2, all before the end of the semester here, so you can see some actual lectures on a whiteboard. Hope you found this helpful. Best to you in the end of the semester.